All right, so recording is on. Welcome everyone to today's workshop on TensorFlow and on neural networks, how to deploy them onto the cloud. Let me know if you can't see the screen. So what we have here is we're going to teach you how to actually deploy and train AI models on the cloud, on Google Cloud. So this is a Pi and AI workshop that is a community workshop organized by our meetup groups, Beginners Machine Learning. So we're a London-based meetup group. We normally run our events in Microsoft Reactor. We're on Meetup, so you can search us if you go on Meetup, Beginners Machine Learning. And my name is Ali Parande. I was a data scientist before becoming a software engineer. I specialize in Python, SQL, and React.js. So I basically build end-to-end programs. So basically what I will be doing today is I will be showing you how you can train and deploy your own AI models with TensorFlow, how you can save it into file disk, and how you can actually deploy it onto cloud. There is a lot to cover in 2 hours, and I don't want to, take your time for 3 hours or whatever. So what I'm going to do is I will cover all the way to training, and if you have time, we can then experiment with how to deploy it. However, I will show you all the deployment concepts you will need to know. Right, so the learning objectives of this workshop is to learn the process of loading and preparing data for training, learning about TensorFlow Eager Execution and how to debug TensorFlow scripts, learning how to evaluate models and common pitfalls that you might have, learn how to perform transfer learning on pre-trained AI models. So that only gives if we have some time. And then we will show you how to learn how to deploy models on the cloud and make predictions. All right. So if you're happy with this workshop, I'm actually building my own courses as well on a platform that I'm building myself called buildyourai.com. So this is still in development, but if any of you guys are interested in doing a trial run of the content I will be producing for this platform, let me know. Basically, the whole purpose of it is to put together a whole AI app from end to end. So you learn SQL, Python, front end, back end, and being able to put it all together yourself. Right. So we will cover data, front end, and back end, and you can have it all in the same place. And you will also have code editors to be able to play around with the code and see the bigger picture instead of going straight into the details and getting bogged down into the mathematics. You can then do some we actually show you the whole tree of knowledge that you need to know, and then you just zoom in different bits and build a whole AI app from beginning to the end. So this is just a platform I'm working on right now, but once it's done, if you guys are interested, let me know, and I can give you some better access to the platform so you can actually go through the content and try to see if you can build your own AI app. So it's going to cover AWS, Google Cloud, and bits of Azure, because each of these cloud platforms have different technologies. Right. Let me just let people in. Right. So before I go forward, does anyone have any questions? All right. So let's talk about the difference between traditional programming and AI programming. With traditional programming, you write your normal scripts. There is some condition statements in there. There are some loop statements in there where you loop over a bunch of files. And basically that's it really. If there is a condition, you just go through that loop. If there isn't a condition, it's just basically you exactly write the script you need to write, right? However, what actually changed the entire landscape was machine learning when it came on. And what machine learning did was that now, instead of having to write the scripts yourself to make that logic happen, you have your data and you know how the input data needs to map to the output data, but you don't know how to make it map. And you use algorithms to map the input data to the output data. So given some input data, you create some kind of model, and then you ask that model, what is your prediction based on this input data. So a lot of companies started using this for giving recommendations to users. A lot of companies started using this to like predict trends, such as in stock market and like house prices and like things like that. So it's very, as long as you have a good amount of data, you can actually build any of your models for your own use cases to start using this going forward, right? So with the same concepts you learn here, you can even like train computer vision models, and you can actually like perform data analysis and things like that as you go forward. But before I go forward, I wanted to talk about biological neurons in action and how exactly they work. So let's go to this is basically where I'm going to be doing some of our drawings for our concepts. I'm just going to share the screen and share the link with you so you can actually go in it yourself. So I'm posting the link in the chat if you want to join the board in your browser. Yeah, Avash, what's your question? It should be top right corner. So if you see my screen, it should be here. Yeah. So I'm gonna basically, most people should be here. So what I'm gonna do is I'm gonna be going on my iPad, and then I'm gonna draw some of these concepts for you. Don't worry if you don't get to do some coding today. These conceptual stuff is actually going to be more important to understand, and then the code, you can always read the documentation. All right. So let me just mirror my screen to my iPad. So this should work now. Yeah. So in your brain, so if this is your brain, well, it's not exactly look like a brain, but if this was your brain, and if we zoom in parts of it, the way your brain works is that you have a bunch of neurons connected to each other like this, and there is a massive network of neurons in your brain, right? When you learn a skill, there is normally a set of signals is passed through one neuron to the other, and a certain pathways keep becoming really active, and as those pathways start sending signals through each other, the amount and thickness of those pathways increase. And there is a saying that like neurons that work together bind together. And for example, if you're learning a skill in piano, in the beginning you don't know what you're doing, but as you learn the skill, certain pathways in in your brain, in your neural network of your brain, become really active, and that basically creates this connections, and those connections like get thicker and thicker and thicker, and it makes it much easier for you to be able to recall that skill and use that skill in the future when you're sitting behind the piano, for example. Okay, so that's the thing I wanted to note. The other thing I want you to note is that normally for a neuron to go from to get activated, the input signals to a neuron need to hit a certain threshold, right? So what I mean by that is, let's say we have 3 neurons that come and connect to a neuron here, right? Now this neuron sends a signal 1, this neuron sends a signal 2, and this neuron sends a signal 3. And basically these add up to a certain value, we call that n. If n is bigger than, like, say 4, then that neuron fires. Otherwise, if these signals are not enough, are not powerful enough, that this neuron will not send any signal to the next one, right? So that's the main premise of how biological neurons work using the threshold, right? So as these other neurons give input to this main one, to this gold neuron, if those signals add up to each other and pass a certain threshold, that neuron fires. Otherwise, this neuron doesn't fire at all. Okay, so that's the main thing, how neurons work in your brain. And the neurons that fire together wire together. So if these neurons, for example, in your neural network, that keep firing together when you're learning a skill, the more they fire together, the more they wire together. So the thickness of those connections start increasing, and allows the signals to go through those connections much easier in the future instance when you practice or when you try to recall that skill. All right, so that's how your brain biologically works, like a simplified version of it. So when research scientists wanted to do like experiments around building something artificial for creating artificial neural networks in the brain, in computers, they noticed this pattern of how humans learn a skill set, and they thought that maybe they could represent this as a mathematical operation so that computers can learn this too. Computers can use this to also learn a skill or find patterns between data sets, right? So that's where the whole computational algorithms around neural networks come into play, and under the hood, TensorFlow uses this logic to create neural networks and train them, basically, right? Which we go into the details of that as well in a moment. But before I go, does anyone have any questions in regards to how biological neurons work, before I go and show you how we go from this to artificial neural networks? All good? Okay. So what we could do is to represent this logic of how your brains work in a way that makes it for us to be able to represent this as a mathematical operation. So there are two things we need to know. One is input neurons, like signal from input neurons, add up, and two, neurons that fire together wire together. So what this means is that the connection between neurons has some kind of weights on them. Okay, so if we represent each of these neurons with A, B, C, D, E, F, G, right? In order to calculate what the data goes through D, we basically say this connection is X, this connection is Y, this connection is Z. AX plus BY plus CZ equals D, because they add up together. Right? So this is A, this is B, this is C, this is X, this is Y, this is Z. So these we call these weights. So these are weights. And A, B, and C are input nodes. Right? And in order for us to understand if D is gonna fire, we need to make this calculation for this specific layer, for this specific neuron, and then understand if we're gonna hit the threshold or not. Right? So that's how scientists try to build artificial neural networks. The whole algorithm for it is basically this. Is you take the inputs and you take the connections as weights, and then you multiply them together. You sum them up, and then you try to see if the output is going to be set, whatever output you get, you then pass it to the next one. And then you just do that for every layer of your neural network, all the way till you get to the end. Right? Now there is a thing here. The only thing that I haven't talked about is that activation function. The whole purpose of that is to add nonlinearity to your code, to the neural network. If you don't put this in, this activation function, after you sum these up, the whole calculation that you do here is linear, right? And why is it bad for it to be linear? It's bad because, let's say, if you have data points like this, there is no way that you can actually separate these data points together with a linear line. Are you going to draw it like this? Are you going to draw it like that? How are you going to draw it in a way so you can separate out these data points? You need some kind of linear function or a linear model to separate out these data points like this. So it's the function, this f of x, that make this happen is non-linear. It needs to be non-linear. Right? So a neural network that is let's say a couple of layers deep, like this, without any activation function, can actually, so let's say this is a neural network, every connection is connected to every other node from each layer, right? So this is a dense neural network. We call it a dense neural network, and these are the hidden layers. This is the input layer, and this is the output layer, right? If we don't put this activation function f of x, so the activation function I talk about is this one. At the end of each node, basically we have a linear model which can be actually summarized by just a neural network that is one layer deep. That's it. And it doesn't let us do much with it. The only kind of model we can get is a linear model. And you can't do much with linear model. You can't map complex data sets to complex outputs with linear models. So that's why you add the activation function at the end of each node when you do this calculation. So basically what you need to do is you put an activation, you pass the D through this to do some kind of activation function. And that activation function has different types. It has sigmoid, you have step functions. You have different types of activation functions that you can decide to apply to that output before you then pass that output out. Right? So what neural networks are actually trying to do is, imagine we have a 3D space, right? There are a bunch of points in this 3D space. Neural networks will try to create a function like a hyperplane that basically separate out these data points in this 3D space, right? So that basically they are separated out into different bits, into different spaces. So these red data points are above the plane, and these yellow data points are below the plane. So they create this plane in a 3D space that allows you to do that. Now the thing is, it's not actually 3D space. There are actually n dimensions. So if this is dimension 1, this is dimension 2, this is dimension 3. Neural networks allow you to actually map data sets that are actually n dimensions. So it could be that many dimensions in the data. You can't even try to understand it or visualize it, because n-dimensional space is like like after 3 dimensions, our brains cannot comprehend it. But imagine an n-dimensional space, and there are data points in that n dimensions. Neural networks, when they're nonlinear, they allow you to create a hyperplane, so that in 3D space, the hyperplane is this is the plane. In n dimensions, you have a hyperplane that like encompasses all of those dimensions. So like imagine it like something like weird, yeah. And then that hyperplane that neural network creates, that is your model, that then given an input, like given an input that is like on like n dimensions like that, like on all these 6 dimensions, it would be able to predict where on the last dimensions the data point will lie. So be able to, for example, be here using that hyperplane. So these are the yellows are the inputs, and the blue is the output when you give it to the neural network, and the hyperplane is the model. It's a bit tough to understand, but basically the main concept is we're trying to separate out our data points in an n-dimensional space. Neural networks allow you to do that. So that, for example, when you try to predict, let's say, give you a good example. Let's say you're trying to predict if a house price is worth buying or not, or if someone is going to default on their credit card. You use their attributes, for example, their sex, their age, where they come from, how much household income they have. All of those are different dimensions of your data. And then when you put those in, based on the past historical data, you have created this like hyperplane model. Your neural network can then predict if this person is likely to default or not. So it gives you the, like, if you fall on the right hand side of this line, you are likely to default. If you lie on the left hand side of the line, you are not likely to default. So think of the neural network as some kind of black box, as some kind of like vault with lots of like knobs and dials on it. And then you give it input data, and then it gives you predictions. Let me make this input data yellow so that it's the same color as the other ones. You give it the input data, and then it gives you predictions. And then if those predictions are not good or are not correct, you basically calculate a loss by taking basically taking your inputs minus predictions, and then based on that loss, you then go and you change these knobs and dials so that this loss comes down. So how do you change these knobs and dials so that like the loss comes down all the way to 0? So you're trying to bring this to 0. And then you just repeat this process. And this whole process of like you going and changing these knobs and dials are basically when you go and change the weights on the neural network. So if this is weight 1, this is weight 2, this is weight 3, weight 4, these weights are the knobs and dials on your black box, which is your neural network. This is on high level how, like in simplified manner, we have tried to conceptualize neural networks in a mathematical form. Right? So, Before I go forward, let's answer some questions. I'm sure you have a lot of questions. Right. So Avash is asking, do you think hyperplane is like a piece of paper or a vector line in 3D? So in 3D, in 1D space, a separator. So if you have a 1D space, a separator is a vertical line, right, that separates out the left and right. In 2D space, it could be like a line like that, or it could be a line like that that separates out data points. In 3D space, it could be a hyperplane. It could be a plane, like imagine like piece of paper that cuts through the space. In higher dimensions, you call this a hyperplane because you can't even visualize it. Like you have like n dimensions, and then like this plane is some kind of like hyperdimensional paper that like can cut through and separate out data points. What is the correlation between hyperplane and weights? So the correlation between hyperplane, so in a so let me show you what the correlation is. So in a let's look at the 2D space, right? So in 2D space, if this is the line that separates out your data points, so let's say these are your data points. How do you define that line? What do you use to define that line? If this is y and this is x, use f of x to define that line, right? F of x, because this is a nonlinear line, could be like ax2 plus bx plus like c or something like that, right? Like some kind of nonlinear quadratic equation. You can use that to define that line. Whatever x you give it, and then you have defined a and b, you can basically give this. If this was just linear, if this was a linear model, the only kind of if your f of x was linear, for example ax plus bx plus c or something like that, your line, let's do it like this. If it was linear, it would be like ax plus b, right? Your line would be like this, basically, something like that. And if you play around with b, it would just go up and down, and if you play around with a, it would just rotate left and right. That's it. And then that's the only thing you could do. With nonlinear lines, you could do more, but with linear lines, you could do less. And with neural networks, you have n dimensions. You could literally fit any plane anywhere you want. And because fitting those planes requires a lot of mathematical operations, like you can't do it by hand, we use computers to do it. And you need a lot of data points to just basically go back. You see this logic I showed you here? You need to just keep iterating over your data and keep changing these knobs and dials, which are the weights, in order to fit the input data to the output data, fit the input layer to the output layer through the weights, in a way that the output layer gives you outputs that has a minimum loss. So the inputs and predictions, the outputs and predictions, this is not input, sorry, this is my bad, this is labels. So labels are basically what you're interested in. So the truth, ground truth, basically we call it. Right, so in a supervised learning, you take the ground truth and you minus the predictions and you have the loss. And what you want to do is you want the predictions to be exactly the same as ground truth, right? So if you're going to say someone is going to default on their credit and you're going to say with a high accuracy, they should default on their credit. Otherwise, your model is not accurate. And you want to keep changing those knobs and dials on your model so that your loss goes all the way down to 0. And the good thing is this loss, you can define it as a function of basically predictions. So what does that mean? If you can define it as a function of predictions, it means that it is looking like a line like this, and you're trying to minimize it. So you want to look for local, you want to look for a global maxima in your loss function. So when you keep changing the knobs and dials, what you want to do, you're moving up and down this hill, and you want to basically get to a point where your loss is minimized. And that's when you say your model has converged. That's when you say your training is done and you've trained a model to the most perfect place you can be. Obviously, if this line goes all the way to 0, that's where you want to be. That's the place you want to get to. And this whole process is called gradient descent, which is an algorithm that actually trains neural networks. So yeah, Stephen, so weights are actually some kind of coefficient that you can play with. And you also have biases. So if we add biases, so we have more parameters to play with, so that we can fit the high. So if you want to move the hyperplane up and down and stuff, we can do it as well, not just like moving it like this. So we also add plates, add biases, which is the B in your equation. Does it make sense? I'm going a bit fast, but if you want me to slow down, I can slow down. All right, so that's basically how neural networks work. Obviously, the loss that you're trying to minimize, which is the difference between your ground truth and your predictions, is not actually unfortunately, it's not actually a simple 2D, it's not a simple function like this that you can figure out and minimize. As always, it's going to be complicated, so it might have more dimensions. Right? So imagine it's 3 dimensions. If it's 3 dimensions, you have like a surface map. Right? It has hills. Let me delete some of this. So it has hills. It has like valleys, and you could start anywhere in this map. You could start anywhere, and your objective is go down the valleys, go down the mountains, all the way down to the valleys. And when you reach the valleys, that's where is your loss minimized. Right? So in 2D, this looks like basically you going down from up here down here. In 3D, you have like more like a map of a 3D map of a space with like valleys and mountains, and you want to go down the mountain basically. And there are algorithms that helps you go down the mountain faster, go down the mountain in the perfect way. And the problem with mountains is that you may go down a valley. So if you're starting from top of the mountain, you may go down and think this is the best place you can be, right? But actually, the best place you can be is here, not there. So this is bad. This is good. You want to be here because here loss is 0. Here loss is let's say 10. Right? So we call this where we call this bit, we call this local minima. And we call this local maxima. Sorry, global minima. No, yeah. No, so yeah, it's global minima. So we call this process, right? So the name of this process is called gradient descent, and it's actually an old process. So there are better algorithms out there, but this is like the most basic way to train neural networks. So what is gradient descent trying to do? First of all, what you do is imagine your neural network is a black box, right? You give it data and you take some predictions. So let's say this is input, and you get the output, and then you take the output, you minus the ground truth. We'll call that T, and then you get your loss. Now what you do afterwards is you take the loss, and then you go back and you see how different weights and biases. So let's say you have like I don't know, 500 weights on your neural network, different layers. You go and try to apply and figure out how each of these weights and biases contribute to the loss, right? And you use something called partial differential equations to do that. So if you remember in maths at high school or uni, a differential equation is just basically the slope of the line. So if this is your f(x), right, and this is y and this is x, df over dy, dy over dx is basically the slope of the line at like a certain point, right? With partial differential equations, you look at, if this was like more than one dimension, you look at how different dimensions contribute to the loss. In dimensions, I mean different weights. So how does different weights of the neural network contribute to the loss? How different connections? And then you go back and figure out how much you need to change this weight. Do you need to go up? Do you need to go down? How much do you go up? How much do you go down? And then you go back and change this. Once you figure that out, you go back and change all the weights and biases on your black box, basically. And then you repeat this process. You do another batch. You send in another batch. Normally, instead of doing one image at a time, you do like 64, because you can use instead of like doing it sequentially, you can do like a matrix of values you can send in, and it mathematically allows you to compute lots of numbers in parallel when you do like a batch of numbers. And you just keep repeating this process until your weights and biases are optimized for that data set. All right. So the next question is, does the model usually use a variety of starting points to find the number of local minima, or is this something you hard code? So very good question, Avash. So let's go back here. Let's say we have a neural network. That's one node, 2 nodes, 3 nodes. Just drawing this sort of say we have a neural network that looks like this, yeah? So if we don't start the weights and biases on this neural network at random numbers, we risk a chance that our neural networks don't converge. So you go back and you change these weights and you keep changing them, and you never reach your local minima. So imagine you have a ball and this is your loss function. So imagine this is your loss. This is basically I don't know, this is like the parameters you change. So you have, let's say you have one parameter you're changing, one weight, right? And you're here, but you when you set, for example, the parameters to a certain value and you don't initialize them randomly, you may end up just being initialized here all the time, and doesn't matter how much you try to go up this hill, you can never do that. You can never come here and go down here. So when you, or another thing that could happen is, if because of the way the maths work, is that like you never end up actually moving left and right at all. Like when you calculate how much you need to move up and down, when you calculate the steps, your up and down is always going to be 0. So you never end up changing any of the weights. So either your ball doesn't move down the hill, or it heals on the wrong it moves on the wrong direction, or you initialize the ball on the wrong part of the hill. So when you initialize the numbers randomly, what that means is that you will always move somewhere. You will always move towards some kind of minimum. You give your neural networks a chance to do that. And how much you go to the right or how much you go to the left, we call this a learning rate. So when I change these weights and biases, do I change them a lot, too much, like really big number, or do I change them a little? Do I change them really big or do I change them a little? We call this a learning rate or alpha. And normally this number should be really small, because if you change it too big, you end up shooting this ball all over the place. It never reaches the minimum. Like you might go down here and then you might go back up here and then you might go down here. So like you never end up like letting it like gradually come down and then like slowly start like getting to the middle of this local minimum of your loss function. All right, so let's go back to the equations. So basically this is how you define a neural network from biological neurons to artificial neurons, as you can see here. And when it's just 3 layers, we call this a non-deep feed-forward neural network. However, for your neural network to do be able to do something like more complex, you need a lot of parameters. What that means is you need a lot of weights and biases. That means you need a lot of layers, basically, right? So designing the architecture of your neural network is also a decision you need to make when you actually try to map your input data to your output data so you can make good predictions, right? So because if you feel like you're actually not fitting the data well, try to add more layers, right? But if you add a lot of layers, what you may end up happening is you may end up do something called overfitting, right? So let me show you what that overfitting looks like. Overfitting is when you actually fit a lot of more data points than you should. So this is what underfitting and overfitting looks like. So in an ideal world, you want to fit your model in a way that you can separate the green and yellow dots, yellow data points perfectly. When you don't train your model enough and you never reach the minimum loss in your loss function, you haven't actually changed the knobs and dials enough, you may end up with a model that actually doesn't separate the data points well or doesn't make good predictions. And if you add too many layers in your architecture, so if you have a lot of like parameters, or you train too much, so that means you change the weights and biases too much, you end up with a model that overfits the data. So what that means is that think of it as a child that like memorizes all the exam questions, memorizes all the homework questions, and then goes to an exam, but then the exam questions are different to homework questions. So instead of like learning the main concepts, this child has actually just learned the exam, the homework answers, and in the exam, the child doesn't actually do well because the child has actually overfitted the homework questions. Does that make sense? So what you want to do is, if you feel like your model is underfitting, add more layers and add more parameters. So you add more knobs and dials. If it's overfitting, either stop training your neural network when it fits, or try to remove layers and reduce the complexity of your neural network architecture. And there is a really good video as well on YouTube from Free Blue One Brown that allows you to actually go and look at it gives you a visualization of how neural networks work, in more detail if you want to understand the mathematics behind it. All right. So that's the math behind it, just so you understand how neural networks work. We are going to actually do some programming to help you get started. So here's an example of images going through neural networks and how each layer sees that image. So basically those images get processed through the neural network, and as you go from left to right, the network, each layer in the network learns different patterns, and then the left side of the network, which is the entry points, the entry layers, learn just like what are the lines are, what are the circles are, what are the dots, where the dots are, and then the outer layers learn the main patterns that would make up, for example, parts of a car or parts of a nose or parts of a face. And then it can then use those patterns to give you the predictions on whether are you looking at a car, are you looking at a ship, are you looking at an airplane, and so on. So this is just an example of how you can use neural networks to teach a computer to see, basically. But there is a Stanford University course that you can actually get your hands into if you want to learn more about it. All right. So let's talk about code. And I think that's enough of theory and concepts for now. So let's talk about code. So there are actually multiple deep learning frameworks that allows you to build neural networks and train them in Python. The most important ones that you can learn is either TensorFlow or PyTorch. Keras used to be a good framework, but then it's more like a library now, where you can build neural networks with it. And TensorFlow has actually wrapped over Keras, and it uses Keras under the hood now to help you build the neural networks. PyTorch is another one that is from Facebook. So TensorFlow is from Google, PyTorch is from Facebook. The way these work are different. However, the way they train neural networks are the same. So both of these frameworks and all of these frameworks under the hood use the same concepts. Right? However, the way they're implemented are different. In TensorFlow is more production ready. It's very optimized for running and training and predicting networks. That's why you see a lot of companies actually implementing their neural networks in TensorFlow. PyTorch is mostly if you want to construct really customized neural networks, really customized like training algorithms, and really customized like predictions workflows. And it's very Pythonic, so you can actually attach a debugger to it, and you can actually see what's happening under the hood. The reason you can still do that with TensorFlow, but you couldn't do it like when it was in version 1 because of something called computation graphs, which I will get into later, what they are and how actually why TensorFlow is using computation graphs under the hood compared to other libraries that just are more Pythonic, I would say. And the reason these libraries are really fast is because mostly they have been built under half of their code base is built with C++ or more. So you see these pink lines. So C++ is literally one of the languages that are very, very close to machine code, binary data machine code. So when you write in C++, you have like very low level access to computer resources such as memory. And you can end up corrupting your memory and stuff. That's because how much low-level code access you have. It's also one of the hardest languages to learn, and it's also one of the most optimized and most performant languages you can see. So when you play PlayStation games, pretty much all those AAA games have been written in C++. And both PyTorch and TensorFlow, they have actually written the libraries and frameworks in C++ so that you can actually do massively parallelized computations, which you need when you're actually working with massive neural networks. So all commercial or all like proper neural networks, so such as VGG and like ResNet and things like that actually do like I don't know, classification and object detection with like 200 labels, they are super deep. They are like 40 layers deep, and they use convolutions. So they use like they use like layers that are even like those layers are very computationally heavy to do. Like you give it an image and it produces like 34 or 64 mini images that are filtered. So think of each convolutional layer as an Instagram filter, basically. But like you get 64 different images of Instagram when you apply that convolution. So with that said, let's have a look at some of the code and let's run a code. So I have an example here. I'm not going to show you the code yet, but I have the demo in my PyCharm. And what this demo does is that it loads the fashion MNIST dataset. Have you guys worked with fashion MNIST before? Do you know what it is? So this is fashion MNIST. So it's a dataset of images of clothes. It has labels and descriptions for each label. So the labels are from 0 to 9. Each of these labels have a description, whether they are t-shirt, trousers. And I think this is about 60,000 images, and all of those images are labeled, basically. And what we want to do is this code builds a neural network that has 1,000 parameters. So think connections and biases, right? Weights and biases, and knobs and dials on the neural network. And of these parameters, this amount is trainable and this amount is non-trainable. So you can freeze some of those weights and biases if you don't want to train them and you don't want to change them. In this instance, we're not going to freeze any parameters. We're going to have all the parameters trainable. And basically what it does, if I run it, it loads the data set, all those 60,000 images. Come on. My laptop's dying. Oh, finally. And it goes through all of those images 10 times. So epochs here represents the number of times you go over each or over all of your data set. So we go all over our data set 10 times, and each time we give a 64 batch of data to the neural network, and then we use that to then go and change their knobs and dials. And as you can see, as we go through each epoch, our accuracy increases from 82% all the way to 91%. And it already starts with a high number because this neural network is actually quite deep. It's like, if I show you, it's lots of parameters on it. It's like a fully dense neural network that has an input of 784 nodes to 128 nodes and then to 10 nodes as the output. And it's quite fast because it's not a big network as such for the computer, but as soon as you start working with images, like big images, then it's going to be much slower to train. You definitely need a GPU. Right? And these are some of the predictions as well from the network. Alright, sorry, I think the connection got dropped. Alright, so before I go forward and we look at the code a bit further, do you guys have any questions? just wait for others to join as well. So while we wait for others to join, does anyone have any questions? That's a good question. So to determine the number of epochs you need to run a neural network, I would say first run it for 1 epoch and see how long it takes. Then run it for 10 epochs with the same settings you have chosen, so the learning rate and things like that, and see how much it's actually improving your accuracy or whatever metric you're using. And then based on that, make a decision around how much epoch you need. Sometimes you don't need that many epochs. The thing is, what you will probably need to do as well is you will need to use something called a tensor board. So TensorFlow comes with a thing called tensor board that allows you to visualize your loss basically and your accuracy. Yeah, you can. So in each epoch, you're basically taking your whole data set, like let's say all those 60,000 images, and you're passing it through the neural network, right? If you do it like a million times, your neural network is definitely going to learn every pattern in those images, and just those images, right? So if you give it any new images now this time, it's going to be like confused because it hasn't properly seen that image because it's learned the wrong patterns basically. All right, so we have 1 more hour. Do you guys want a break before we go more into the code, or do you want me to continue? You can take a 5-minute break if you want to grab coffee or like anything. Yeah, sounds good. Because yeah, I think a break would be good because then if you go to the code stuff, then you have like some energy as well. So I would say instead of 5, let's come back at 7:15. So 7:15, I'll just post it in the chat, and then I will start to show you how TensorFlow API works. So my mission is by end of this session, you should be able to feel more comfortable playing around with TensorFlow, and try to see if you can build your own models with TensorFlow using the TensorFlow APIs. So you will learn how the TensorFlow APIs work in the next hour. See you in 10.